Okay, so the logarithmic laws. So now there's three main log laws that we use, and then some results that come out from the fact that these log laws exist, and other things because of properties of index or indices that we know. So let's start off with the three log laws. So the product rule, or the product law, we should say, not the product rule because that comes up later. Log A of xy is equal to log A of x plus log A of y. So for example, if we had log base 2 of 8, well that's the same as log base 2 of 4 plus log base 2, I'll put EG, of 2. Okay? So pretty straightforward. And that comes from the idea of the index and indices. So 2 to the power of 2 times 2 to the power of 1 is the same as 2 to the power of 3. So you just add the index. So 2 plus 4 index. Okay, so that's the product law. Now we're going to go with the quotient. Now the quotient law says if we have log of some base of x divided by y, and that is just the difference of the two, like that. So for example, if we had log of 2 of 4, then we can say that's the same as log of 2 of 8 minus log of 2 of 2. Again, it might be, the reason why we're doing it like this is, again, it can be written either way. So, if you've been given this side, you can turn it back into this one and vice versa as well. So these two are interchangeable. I am just showing you how they are, or what they are, and an example of each of these. And then the third one we've got is the log of a power. So if we have log, we should write that actually, log of a power. So log, well, geez, I can't seem to get this right. So power law. And that is, if we have log A of x to the power of, or x to some power, let's say n, well that's the same as n lots of log A of x, okay? So basically the power just comes down the front. And so an example of that too, okay? So if we have log A, not A, let's use something else, a number. If we have log 3 of 27, well that's the same as log 3 of 3 to the power of 3, which is just then 3 log 3 of 3. Now that's a very, very, very useful one, and it's going to be popping up a lot, particularly later on. Now, some particular values of logarithmic functions. So, some particular ones that we're going to have. So, log of any base of 1 is always equal to 0, because anything to the power of 0 is equal to 1. Okay, so that's the first one. The second one we've got is log of some base of that same value. Well, that's just equal to 1. Okay, so again, anything to the power of 1 is just its thing itself. Okay, and I can write next to it too, because a to the power of 0 is equal to 1, and a to the power of 1 is equal to a. Now the next one that we've got is log a of root a is equal to a half, okay? And that's because the square root of a is equal to a to the power of a half. Okay, and the next one we've got is log a of 1 on a, and that is equal to -1, and that is because 1 over a is the same as a to the -1, okay? So you can see why a lot of these log laws exist, it's just some of the results that we've come up with before. And now let's say we have log a of a different value, 1 over a different value, then that's equal to negative log a of x. Now the reason for this one Now this one's a little bit different, is because if we had log a of 1 on x, then that's the same as log a of x to the negative 1. And then using that power rule from above, that's the same as negative 1 or negative 1 of log of a of x using that power rule. Okay. Now, logarithmic and exponential functions are inverse functions. So the inverse of an exponential is the log, and the log is the inverse of the exponential. Okay, so if we let the base a of any positive real number not be equal to 1, then two other important ones we've got are log a of a to the x is just equal to x. Okay, and also that a to the power of log a to the x is also just equal to x. Okay, and the top one is for all real x, and this one is for all x greater than 0. Okay, so those two statements are also true. Okay, so basically if we ever have log of some base of then a to the power of x, it's just equal to x. You can prove this top one here by using the power of a power, or the log power rule, and the fact that a of a, so like this one here, is just equal to 1. And the second one is a little bit trickier to show, and we'll be dealing with that sort of stuff a bit later on and why it's useful a bit later on. So let's have a look at some examples of these. So here's the logarithms. So example number, I forgot to change it. So example 1. Simplify the following using log laws. So let's start with part A. So we've got log 5 of 50 minus log 5 of 25. So log 5 of 50 minus log 5 of 2. So that's just equal to, so using the subtraction one, it's going to be 50 over 2. Okay, dividing them because they've got the same base. So this is the same as log 5 of 25. So what to the power of 5 to the power of what is equal to 25? So the answer to this one is just 2. Okay, so the second one we've got log 2 of 16 plus log 2 of 4. Okay, so we're adding these ones, so we use the product, or the product, so 16 times 4. Okay, so that's equal to log 2 of 16 times 4, which is 32, so it's 64. So this is 2 to the power of what is equal to 64. Well, that's just 6, so another nice and easy one for us. Now this one here, we've got 2 log 5 of 5. Okay, we can use the fact that log 5 of 5 is equal to 1, so to get an answer of 2, so we can verify it that way, or alternatively using the index law. This is the same as log 5 of 5 to the 2, okay, which is the same as log 5 of 25. So 5 to the power of what is equal to 25, so that one is just 2 as well. Okay, so again, we could also say that, well, we know that 2 log 5 of 5 is equal to 2 times 1, okay, which is just 2 in that case too. So that's why it's useful to go back and forth. You can verify it in a bunch of different ways. Okay, it makes it easiest for us to see. Simplify the following. Okay, so we've got some now that we can actually simplify using these rules. So we've got A is log 5 of 5 to the 2, and B is log 7 to 7 to the 6. So we'll start with A, and it's very similar to the one that we just did on the other side, 5 to 2. So we could do 5 squared and work it out that way, or we could use our log laws and say, well, this is the same as 2 lots of log 5 to the 5. Now, because log 5 of the 5 is just equal to 1, this is the same as 2 times 1. So it's equal to 2. And I'll write here as log 5 to the 5 is equal to 1. Okay, now with B, same sort of thing we're going to do. And it's nice that they've left this in index form for us. So log 7 to the 7 of 6 is the same as 6 log 7 of 7, which is the same as 6 times 1, due to that same thing, log 7 of 7 is equal to 1, so this one is just equal to 6. So that one is also nice and straightforward for us too. Okay, write 8 as a power of 12. Okay, so to write 8 as a power of 12, we're just going to say, okay, 8 to the power of 12 is equal to x. So writing 8 as a power of 12. Oh, sorry, no, that's not right. Oh, jeez. Writing 8 as a power of 12. 8 is equal to x to the power of 12. There we go. So 8 is equal to x to the power of 12. And that's all it means by that. So we're just writing it in that way. So it's a worded problem that we're going to write like that. We're not actually asked to solve it, we're just asked to write it. So 8 is equal to x to the power of 12. I think it's actually meant to be like this. There we go. Power of 12. That's better. Then part B. Write 9 as a logarithm base 4. Okay, so 9 is equal to log base 4 of x. So just like that. Okay, and that's it for those ones. So obviously not the hardest questions, but I just needed to show you what these ones look like so that you could actually answer them. Because if you don't know how to answer them, then what's the point? Okay, now these ones are cool ones because we're going to use some log laws to work them out. And because we've actually been given values, so that log 7 of 2 is approximately equal to 0.36, and log 7 of 5 is roughly equal to 0.83, we can actually give estimations of some other values. So if we look at part A, we've got log 7 of 10. Now log 7 of 10 is the same as writing log 7 of 2 times 5. And we know using our our log laws, that this is the same as log 7 of 2 plus log 7 of 5. Okay. Now we know log 7 of 2 is approximately equal to 0.36, so there should be an approximately symbol here. Plus log 7 of 5, which is approximately equal to, log, which is approximately equal to 0.83. Okay. So then that for that, this is approximately equal to, it's not going to be 0, it's going to be 1.19. So log 7 of 10 is approximately equal to 1.19. And we can test that as well by using the calculator, my special one. Put the 10 in, hit equals, and there we go, 1.18. 183. So again, it is an approximation, okay? So it's not exact, but it's relatively close, which is awesome. Now part B says log 7 of 2 on 5, okay? Well, we know that this is the same as log of 7 of 2 minus log 7 of 5, okay? So we can we can now substitute our values in because we know that they're approximately equal to 0.36 minus 0.83 because that's what they're approximately equal to, and therefore log 7 of 2 on 5 is approximately equal to, I'm going to use the calculator for this one because I can't think right now, 0.36 minus 0.83, and that's equal to approximately negative 47 on 100, so approximately negative 0.47. So if we put this in the calculator again, so log 7 of 2 on 5, hit equals, there you go, it's approximately equal to that, which is awesome. Now we've got log 7 of 20 for part C. Log 7 of 20. So that's approximately equal to, that is equal to log 7 of, okay, so how are we going to do this one? Well, it's the same as log of 4 plus log of 5, okay? So 4 times 5, which is 20. Okay, and we know what the log value of 5 is, but we don't know what the log value of 4 is. But we do know that log 7 of 4 is equal to 2 squared. Okay, should be a 7 there. Of 5, okay. So we can rewrite this as 2 log 7 of 2 plus log 7 of 5. Okay, so that's 2 times, well, this is approximately equal to 2 times 0.36 plus 0.83. Now you might be saying, well, you know, we could have, instead of doing log 4, we could have done log 2 plus 2 and then have 2 log 2s. It's going to give us the same value regardless. Okay, I'm just showing you that we can do it a different way using that value there. So I'm going to put this one into calculator because I'm lazy. Hit equals, and we're going to get 31 over 20, which is approximately 1.55. So again, we're going to verify this one, so it should be log 7 of 20. And 1.54. Okay, so again, they're not going to be exact because these are approximations from the beginning, so like those values are approximations, but it's a good way to get approximations down. Now let's do the last one, which is part D. Log 7 of 14. So log 7 of 14. Now that's approximately equal to log 7 of 2 times 7. Sorry, that is equal to that, which is equal to log 7 of 2 plus log 7 of 7. And you might notice that we've got a log 7 of 7, so that's just equal to 1. So log 7 of 2 is equal to 0.36. This is approximately, plus even though the log 7 of 7 is exactly 1, the 0.36 is still an approximation. So this should be approximately equal to 1.36. And again, we can verify log 7 of 14. 1.36 if we round it up. Cool. Okay, so again, that's just applying log laws and using the facts that we've got an approximation there to then substitute those values in. That pretty much brings us to the end of this section, so the laws of logarithms. Okay, and then next we'll actually have a look at some equations involving logarithms. So stay tuned.